Have you ever wondered what happens when a star's mass becomes too great for it to handle? This is the question that takes us on a journey through the cosmos, into the heart of a star. A star's life is a grand spectacle, a tale that unfolds over billions of years, and at its heart, it's all about mass. You see, a star's destiny is intrinsically entwined with its mass. The mass of a star is far from a static property. Instead, it's an ever-changing dynamic factor that shapes the course of the star's life. As a star continues to accumulate mass, the gravitational pressure at its core increases proportionally. It's a delicate balance, a cosmic dance between gravity and the star's internal forces. Now, you might be wondering what happens when this balance tips. Well, that's where things get really interesting. When the mass of a star reaches a certain threshold, a critical point is touched upon. At this juncture, the temperature or density at the star's core becomes so high that it triggers a profound and dramatic event, the gravitational collapse. But what exactly is this gravitational collapse? It's a process that happens when the gravitational forces within a star become so strong that they overpower the star's internal pressure. When this happens, the star can no longer support its own weight, and it begins to shrink under the influence of its own gravity. It's a pivotal moment in the life of a star, a point of no return that marks the beginning of the end. This, my friends, is the crux of our cosmic tale. It's a narrative of balance and imbalance, of gravity and pressure, of creation and destruction. It's the story of how stars live, change, and ultimately meet their end. And it all rests on the seemingly simple yet immensely powerful concept of mass. And this is where the fascinating process of gravitational collapse begins. In the vast interstellar clouds, a delicate balance holds the key to star formation. Imagine a serene expanse where gas particles drift in a gentle dance. This dance is governed by a principle known as hydrostatic equilibrium. It's a state where the kinetic energy from gas pressure perfectly balances the potential energy of internal gravitational forces. It's like a cosmic waltz, where each partner, gravity and pressure, keeps the other in check. Now, imagine this dance expressed mathematically. This is where the virial theorem comes into play. It's a rule that states the gravitational potential energy of the cloud must equal twice its internal thermal energy. It's like a cosmic equation, balancing on the precipice of creation. But what happens when the balance shifts? Well, if a pocket of gas in the cloud exceeds a certain limit, a critical mass known as the Jeans mass, the equilibrium is disrupted. The scale tips in favor of gravity, and the cloud begins to collapse. It's as if the dance partners tripped, spiraling towards the dance floor in a dramatic plunge. This collapse isn't a calamity, though. Instead, it's the genesis of a new star. The gravitational forces pull the gas particles closer and closer together, increasing the density and temperature at the heart of the cloud. The pressure mounts, heat intensifies, and the core of the cloud lights up. It's like a cosmic sparkler, its radiant glow marking the birth of a new star. This process, from hydrostatic equilibrium to gravitational collapse, is the cradle of star formation. It's the cosmic nursery where stars are born, their light destined to twinkle in the night sky. But remember, this is just the beginning. Once a star is born, its life is a constant struggle against gravity. The newly formed star must maintain its own hydrostatic equilibrium to prevent further collapse. And when it can no longer sustain this balance, the star may meet its end in another, more dramatic gravitational collapse. As the cloud collapses, a new star is born, setting the stage for a possible future gravitational collapse. As the star exhausts its nuclear fuel, its core contracts, leading to a fascinating transformation. This is the final act in the life of a star, where the outcome hinges on the mass it carried throughout its lifetime. Imagine it as a cosmic crossroads, with three possible paths: becoming a white dwarf, a neutron star, or a black hole. Let's first step onto the path of white dwarfs. These celestial remnants are the outcome of low to medium mass stars that have exhausted their nuclear fuel. The core of these stars contracts, while their outer envelope disperses over tens of thousands of years, creating a breathtaking spectacle known as a planetary nebula. These white dwarfs are supported by a pressure known as electron degeneracy pressure. It's a quantum mechanical phenomenon that arises when electrons, which are fermions, cannot occupy the same quantum state simultaneously. In some cases, if a white dwarf has a companion star, it can start to accrete or draw off matter from it, leading to an entirely different sequence of events. Now, let's venture down the path of neutron stars. These are the remnants of massive stars which collapse under their own gravity after they've exhausted their nuclear fuel. In this scenario, the gravitational pressure is so intense that it forces protons and electrons to merge into neutrons. The result is a neutron star, an incredibly dense object that resists collapse through neutron degeneracy pressure and short-range repulsive interactions mediated by the strong force. These stars are so dense that a sugar cube-sized amount of neutron star material would weigh about as much as a mountain. Lastly, we face the most enigmatic path, the creation of a black hole. When a star is so massive that no force can withstand the pull of its gravity, it collapses into a black hole. The core of the star becomes a point of infinite density, known as a singularity. This singularity is shrouded by an event horizon, a boundary from which not even light can escape. Thus, a black hole is born, an entity so dense and with such strong gravity that it warps the fabric of space-time itself. Each of these outcomes, white dwarf, neutron star, and black hole, results from the same fundamental process, gravitational collapse. The mass of the star determines which path it will take, and the result is a unique remnant with its own set of characteristics. But it's not just about the end result. It's about the journey that the star takes, the transformation it undergoes, and the profound effects it has on its surroundings. Whether it's a white dwarf slowly cooling over billions of years, a neutron star spinning at incredible speeds and emitting beams of radiation, or a black hole warping space-time and swallowing everything that ventures too close, each of these remnants tells a unique story of a star's life and death, all driven by the relentless force of gravity. As we gaze at the night sky, we are witnessing the echoes of countless gravitational collapses. These collapses, these profound cosmic events, are the very keystones of the universe's celestial architecture. Each twinkling star, each nebulous cloud, and each enigmatic black hole are all testament to the power of gravity's relentless pull. Let's consider the birth of stars, a process that reveals the gravity's might in all its glory. In the serene expanse of interstellar clouds, a delicate dance unfolds. When a pocket of gas exceeds a critical mass, gravity takes the lead, pulling together the particles, condensing them into a fiery ball of plasma. This is the birth of a star, a newborn light in the cosmic darkness, all thanks to gravitational collapse. But what about the remnants of cosmic giants, the stellar remnants left behind after a star's grand finale? These too bear the hallmarks of gravitational collapse. Take white dwarfs, for example. These are the remnants of low to medium mass stars, compacted into dense cores by the force of gravity. Neutron stars, born from more massive stars, resist collapse through neutron degeneracy pressure. Yet they owe their extreme density to the gravitational collapse of protons and electrons into neutrons. And then, of course, there are the black holes, the universe's most enigmatic objects. These are the result of gravitational collapse in its most extreme form. When a star's mass is so great that no force can withstand gravity's relentless pull, it collapses into a black hole. The core becomes a singularity, a point of infinite density, hidden within an event horizon from which not even light can escape. These cosmic phenomena, from the birth of stars to the formation of black holes, are all echoes of gravitational collapse. They are the universe's way of demonstrating the cosmic cycle of creation and destruction, all orchestrated by gravity. In the vast cosmic theater, gravity plays the leading role, orchestrating a timeless saga across the fabric of space-time.